ready to move on? We're going to do implicit differentiation today, or you're going to learn how to do it. And this just takes everything else just one step further. One thing we're going to do is expand our vistas when it comes to differentiation. The other thing is we're going to get ready for something really interesting in the next section called related rates. So implicit differentiation, well, don't be scared. We're not starting a whole new project on you. Instead, we're just tweaking it just a little bit so that you can do even more differentiation. So what do we want to do? Well, we want to find derivatives explicitly. Hey, guess what? That's exactly what we've been doing so far. Well, that objective is covered, except we're going to take a look at it. Then we're going to find derivatives implicitly. And I'll explain what that means. But basically, it includes, if you think of the explicit ones up here, usually you start out with y equals, let's just throw something out here. Y equals, and then something with an expression that has x in it. When we're doing it implicitly, that means that we don't have y equals. We could have something like this. And we're trying to differentiate. The catch is with this one, if you look at it carefully, if you try to make this into something like that, you're stuck. You can't do it. Solve this for y squared, that's fine, but not for y. So we could be caught in a conundrum. Instead, we're going to take care of that right now. And then we're going to use it to answer questions, real life questions, situations. So here's just a couple of pictures, really. This gives you an idea of implicit differentiation. And if you look carefully, you can see something similar to what I just mentioned. X squared plus y squared equals 1. That does not set it up for doing explicit differentiation, because it's not a function. What we've been differentiating are functions. This is not a function because if you pick an x, it gives you 2 y's instead of just 1. Not a function. We're going to get past that. Here's another example with the 25 there, and an example of how it's done. We'll talk about that real quickly. So this is the explicit form where y equals, and then what you've got on the right hand side is some expression about x using x. Here's a real quick example. Y is a function of x. These are all constants and x's. Since it's written explicitly as a function of x, we can differentiate it without any trouble. But not all of them are nice like that. So let's start off with something a little bit simpler. Do y dx for the equation xy equals 1. Maybe I dare you to pause this and see if you can differentiate this with respect to x. You actually have all the skills you need. You don't think so? Well, let's take this. Remember our friend rewrite? Well, we can rewrite this by dividing both sides by x. Look at y equals 1 over x. Rewrite that again. And we're ready to go. Does that look familiar? dy dx equals, bring that minus 1 out front, reduce that minus 1 by a single one, and what we've got is dy dx, negative 1 over x squared. Since we can change it so it's explicitly defined, we can actually do this. But as it stands here, it's implicitly defined. But not all rewriting will do that for us. There's another interpretation here. Same thing. There we go. The rewrite and the derivative and the final rewrite to make it look in its best form. So that works sometimes if you can rewrite it so that it's got an explicit function in terms of y. However, if you can't do that, what do? Well, you're going to use all your skills that you've had so far and just one simple one that you're going to add right now. You can see that if we're going to differentiate with respect to x, this first one's going to be pretty easy. That's easy, that's easy. This one, not so much. However, think chain rule. As I mentioned before, the chain rule is another one of your big friends. Always think chain rule, and you can't go wrong. Even if you don't need to use it, it won't get you into trouble. So how do we do that? Here's another one. That would be another problem. You can't write this in terms of y equals and just an expression with x. What you need now is implicit differentiation to take your differentiation to another level. So here we go. To do that, you have to recognize what's happening with respect to x. That's important. With respect to x. That's what you've been doing all along, with the small exceptions of with respect to t occasionally. We're going to take this one step further. You can do the same thing as you did before, but that chain rule is going to take you to the next level. Watch through this next example. Notice how the chain rule is used to introduce the dy dx factors where you didn't expect them. So let's take each one of these and differentiate it with respect to x. So I'm going to steal some space here. We're going to start with 3x squared, and we're going to differentiate that. Well, of course, this represents y equals dy dx. And our dy dx, bring that 2 out front. I hope you do have this automatic, right? 6x, there's your derivative. Part B, you have 2y cubed. Now here's where it gets interesting. Here's where you move to the next level. Now if you're doing this with respect to y, it'll be pretty easy. Well, start out that way, but remember the chain rule. So bring that 3 out front. Now you've got 6. Y cubed becomes y squared. So far, so good. But remember, y is a function, and it's not with respect to x. So we'll have y prime or dy dx. In other words, you're using the chain rule to take the derivative of y. That's all there is to it. Do this as you would the x. And if you've got something that isn't an x here, then you'll have d, in this case y, with respect to x. That's part B. Part C, we're starting out with x plus 3y, and we're going to differentiate that. X, pretty easy, 1. Now, if you're thinking chain rule, you might say, but x, isn't that a function? Yes, it is. And what's the derivative of that? It's dx dx. Well, that's a 1, right? Next, the 3y plus, Okay, remember there's a 1 out here, so 1 times 3 is 3. That's no big deal. But remember, y is a function. So chain rule says the derivative of that with respect to x is dy dx. And there you have it. 1 plus 3 dy dx. You're getting there. Part D. Okay, here's where you pick up another one. Remember the product and quotient rules? We've got a product right here. So let's start out with this one and keep it simple. X, and then we're going to take the derivative of y squared. Product rule plus. Now we'll reverse the roles. X, we'll take the derivative of that times y squared, no derivative. Now, let's get to work. X is just x. Good. Y squared. Well, let's see. Bring that 2 out front, and I'll slide it the whole way out here. Y to the what? Subtract 1 from the 2. There's our y. And chain rule, dy dx. Get used to that. Chain rule says take the derivative of this y plus. Now what do we have out here? The derivative of x with respect to x is 1. Leave that off for now unless we need it. And the second part, just y squared. 1 times y squared, y squared. There is our derivative. Something we couldn't do just 1 week ago. Let me clear that slide out of the markers. There we go. So, a quick review of what I just did. 3x squared, just as normal. I hope you can do this in your sleep, right? Second one, 2y squared, a little bit different. Yes, bring the 3 out front, multiply it times the 2, reduce the 3 to a 2, and there's your derivative, all stretched out, simplified. There you go. Remember, chain rule, because this y right here, you have to take the derivative of that by itself, and that's where you get the dy dx. Third one, the sum rule. We're putting everything together right now. There's 2 derivatives. You take the derivative of the x, then the derivative of the 3y. Just work them separately. Put them on a separate sheet of paper if you need to, although you probably won't need to. The derivative of x with respect to x, 1. dx dx, of course. dx dx. If you're really a slave to the chain rule, and in a way you should be, dx dx is 1. So 1 times 1 is 1. There you go. But remember, chain rule, chain rule, chain rule. Second part, take the derivative of 3y. If that were a 3x, you'd just get 3. You get the 3. But since y is not an x, then you make it dy dx, because you're taking the derivative of y, which is dy dx. And the fourth one, product rule. So you're going to have plus between them. Remember, you've got the first part times the derivative of the second, and derivative of the first times the second. Product rule. And there you go. A little bit of simplification, please. There we go. All right. Here are the guidelines. Let's see. So if you want to do this, let's create something. Let's say we've got 4x plus 3y squared equals x cubed plus 2y. How about that? And we want to find dy dx. First of all, differentiate both sides of the equation with respect to x. All right, so take the derivative of the 4x, 4. Easy enough. Next, 3y squared. Notice there's a y here, not an x. But start out as normal. 2 times 3, you get the 6. Y becomes a y. 2 minus 1 is 1. And y is not an x, so we'll have a dy dx here. By the way, ignore that. That's a 1, not an apostrophe. Equals. Keep on going on the other side. X cubed, automatic. 3x squared plus, I'm going to have to squeeze this in here, 2y. If we were doing this on x, we just have a 2 there, but we have to take the derivative of the y according to the chain rule. So we'll have dy dx. Squeeze that in there. Got it all? Okay, second. Write that so that all the terms involving that are on the left side. So I guess I'm going to have to do this a little bit differently. All right, so what you want are all dy dx terms on the left side. Well, where are they? Well, let's take one piece at a time. This y doesn't, or this 4 doesn't have a dy dx, so we'll have negative 4 on the other side. The second term does have a dy dx, so 6y dy dx goes on the left side, where it is. Over here, the 3x squared doesn't have a dy dx, so we'll leave it where it is. And then the last one, 2 dy dx, has a dy dx. We'll bring it over to the other side, and we'll squeeze it in here. Minus 2 dy dx. And there's our equation. Squeezed in. I think you get the point. Now, the next thing you do is factor out the dy dx on the left side. So the left side, both of those terms, as we intended, have dy dx. Factoring out the dy dx, we have 6y minus 2. There's the left-hand side, and the right-hand side, we'll reverse those terms because I like it that way, not because it has to be. Last of all, that factor that we have in back of the dy dx, divide both sides by the 6y minus 2. So we'll end up with dy dx equals, we've got 3x squared minus 4 on the other side, divided by the 6y minus 2. And there we go. We have dy dx. Even though when you look at this initially, you say, oh, 2 days ago I couldn't have done that. Can I do it now? Well, now you can. You can find dy dx, even though it looks as though from the perspective 2 days ago, I can't do that. Now you can. There's your dy dx. And if you had a step 5, usually that would involve something like, how is y changing? And you would be interested in maybe at the point 5, 2. So what you would do to get dy dx at 5, 2 would be to put the 5 in where the x is, the 2 where the y is, and evaluate that expression. That's all there is to it. So you can get that dy dx even if you have both x and y, like we did. So here's another one, and we're going to take a look at this. Notice this is not an equation that you can solve for y. Sorry. But with the implicit differentiation, we can actually take this. So we'll differentiate both sides of the equation. That's step number 1. So differentiate each of those terms. What does that look like? Well, there's the y cubed part, and there's the y squared part, 5y minus 5y part. We're just setting it up. Do this so that you can concentrate on the details. Now you'll actually take the derivatives of each one of those parts of the sum or difference. Next, we actually do it. First one, bring that 3 out front, drop the 3 to a 2 in the exponent, and since this isn't x and we're differentiating with respect to x, dy dx becomes part of your family. Next one, a little bit more practice of the same sort. 2 out front becomes y to the first, and since this is a y and not an x, put it into dy dx. Next one, you have a 1 here as an exponent, bring it out front, or actually not, use one of the rules. So you have minus 5, and since this isn't an x, you put dy dx there. And then differentiate this one. That's a simple one. There's no y there. Minus 2x, and on the other side, the derivative of a constant. This is a nice summary of all our rules, right? All right, what's next? We've taken the derivative of each of the individual terms. Now what do? We get all the dy dx terms on one side. That means all 3 of these are going to be on the left, and this we're going to move to the right. There you go. What's next? We're going to factor out all these dy dx's. There you go. Dy dx, and what remains after you factor it out? And your lonely 2x over there. Now, how do you get dy dx? Divide both sides by the factor of dy dx. And what you have now is dy dx. You've done it. Implicit differentiation at your service. This is how that equation actually looks. Not a function. You can tell it's not a function. Remember functions? Oops, it's not a very straight vertical line. There's a vertical line that crosses it at 2 points. That means it's 3 points. It's not a function. However, even though it's not a function, we can use implicit differentiation to find the slope at any point on that curve, even though we couldn't just a day ago. How about this? All right. So if you want the slope at 1, negative 3, put the 1 in here where the x is, put the negative 3 in where the y's are, and just plug them in. Simplify, and there's your slope at the point 1, negative 3. Other points, probably different. At the point 1, negative 3, the slope is 1/8. In fact, if we sneak back here, here's the point 1, 3. Notice the slope of the tangent is rather shallow, but it's positive, but rather shallow. That's why the slope here is positive, but very small. So how about this one? Maybe you could pause the video and see if you can do this yourself. All right, are you back? Did you give it a shot? Come on, you can do it. I'll give you another second to pause this and try it. All right, you're back. Let's, first of all, we want to find dy dx. So here's the original equation from there. Now we're going to take the derivative with respect to x. of everything there. So this first one, 4x, that should be a piece of cake. Second, bring that 2 out front, you get the 2y. But this isn't x, so you need the dy dx factor. On the other side, taking the derivative, 0 of course, because you've got a constant. Now, subtract 4x from both sides because you want all the dy dx terms on the left by themselves. Next, divide by the negative 2y because you want dy dx, and there you are. dy dx at any point on that curve. But what are we interested in? We're interested in what dy dx is, or the slope is, at point 1, 1. So we'll just put 1 in for x, 1 in for y, and there's our slope. Our slope is 2, and if you look at the picture over here, here's the point 1, 1, there's your graph, it's a hyperbola, and the slope there, you can tell, is on the steep side. It's also positive, just like you would expect a slope of 2. All right, let's wrap this up with a short application. Here's the demand function. Now, I know this looks a little bit weird because this is in terms of price equals. And this is actually the demand in thousands of units. Be careful about that. When you get the answer for x, it's in thousands of units. We've got a small problem here. We don't have this in terms of y, or in this case, we want to get it the rate of change of the demand, that's x. So what we want with respect to p, so what we want is dx dp. You have to figure this out. Dx dp is what you need. So dp is what we're differentiating with respect to. So we're going to take this equation and find dx dp. First of all, there's our original equation. We're going to rewrite this just slightly. We're going to write it like this so that the p is on one side by itself. That's going to be handy because we want dx dp, and the p is on this side. So what do we get? Okay, let's differentiate with respect to p. All right, now does this look weird? Maybe, because you're not accustomed to this yet. But if you look at this first term, one right here, bring that 3 out front, multiply it times the point 0.00001, and there's your point 0.00003. Okay, good? Now you drop that 3. Sorry about the alarm. It's time to wake up, I guess. Okay, so this is what you would call the normal part, but you're not differentiating with respect to x, you're differentiating with respect to p. So this x needs differentiated as well. Chain rule, remember that? Since we don't have dx dx, it's going to be dx dp, and it doesn't go away. Plus, okay, imagine there's a 1 here. 1 times this 0.01, 0.01. Easy. Chain rule, we're differentiating with respect to p, so this becomes dx dp. If this were p, then we would have dp dp, and we wouldn't need it at all. Third, the derivative of any constant, 0, so you don't see anything there. On the other side, remember, you can take that 3 over p and rewrite it as 3p minus 1 and differentiate it. We're just sneaking off to the side here a little bit. Bring that minus 1 out front. You have negative 3, p to the negative 2. Remember, you're subtracting 1, so you have negative 2. And what's that look like? It looks like this. -3 over p squared. And what about the p? Well, we're differentiating with respect to p, so it's dp dp, which is still 1, no matter how you look at it. What's next? Well, we have all the dx dp's on the left side, so we factor out the dx dp, and then we'll divide by the factor of dx dp, which will end up being in the denominator. There is dx dp, exactly what we wanted. Now, what we want in particular is when the demand is 100. The demand is 100. The price is, and we can use our original equation to find out what the price is. Price is $1. Now keep in mind, I know you've forgotten this, or I'm almost sure, this 100 actually is 100,000, because remember the demand was in thousands. But for our equations, we're just using the 100 part of it. So we've got x, we've got p. We'll put it in our dx dp to find out how the rate of change of demand with respect to price is. There's our 3 that was on top there. We just put our x and our p, and the rate of change of demand with respect to price is -75. Now translate that. Remember, x is in thousands, p is in dollars. So when x equals 100, the demand is dropping at 75,000 units for every dollar increase in price.